Bismillahirrahmanirrahim. Assalamu alaikum, dear students. We are now starting the second lecture for the fourth week of the course Wireless and Mobile Communication. Actually, this lecture is in continuation with our previous lecture. In our last lecture, we talked about trunking system, and we discussed that there are two types of trunking system. We named them as blocked called cleared system, and second one as blocked called queued system. Sometimes we call them Erlang B and Erlang C systems. For one of the system, if all the channels are busy, in that case new caller is denied access to the system. So grade of service for that particular type or a long B type systems is the probability of blocking. And for the second system, if all the channels in the system are busy and a new caller arrives, it is put on hold or in a queue until a channel becomes free. In this particular case of system, the probability of delay greater than some specific amount of time is the grade of service for that system. So these were two types of system that we discussed in our last class, and we started doing some problems based on these Erlang B and Erlang C types of systems. So we are continuing that discussion with some new problems. So we are taking the problem which is example number 2.5 in our textbook. So this one, the problem states that an urban area has a population of 2 million residents. So this thing indicates that the total population is 2 million, and for that 2 million population there are three competing trunk mobile networks named as system A, B and C. So we can assume that there are three different service providers who have made a trunk mobile cellular network to provide coverage in the area which is residence of this 2 million population. Of course, because these are three different systems, so they have three different implementations which are defined in the problem. System A has 394 cells with 19 channels each. System B has 98 cells with 57 channels each, and system C has 49 cells with 100 channels each. So each of the system is defined by a specific number of cells in the area, and each cell has a specific number of channels. We want to find the number of users for this particular case, where we want to have a probability of blocking of 2%. Probability of blocking of 2% indicates that this system is actually an Erlang B system, because in that case we are interested in looking at the blocking probability, not the delay probability. The next condition given in the problem is that each user averages 2 calls per hour with at an average rate of 3 minutes, average call duration of 3 minutes. So this will provide you an indication of what the per user call traffic intensity is there. So we want to find number of users for all these three types of system. Secondly, if we assume that systems are operating at maximum capacity, we also want to compute the percentage of market penetration for each type of cellular provider. So there are two tasks. So first we focus on the first task, which is finding the number of users for each type of systems. So let us begin the solution. So we start with system A. We are given that probability of blocking that we need to focus is 2%, which is actually 2 divided by 100, that is 0.02. For system A, the number of channel in a cell is given as c is equal to 19. And second thing is this condition of how users are making calls in the cell. So this will give you traffic intensity per user, which is by definition product of lambda and h, where lambda is given as the arrival rate, which is mentioned here as average 2 calls per hour. So we have 2 calls per hour, lambda is 2, and the call duration, average duration is 3 minutes. So h, which is mean holding time, is 3 minutes, and we are calculating on per hour basis, and 1 hour has 60 seconds, therefore we have to divide it by 60. So we get the traffic intensity per user of 0.1 Erlang for this system, and this traffic intensity is same for all types of systems because it's the same condition for A, B and C. So for system A, now we know the grade of service is 0.02 and number of channels per cell is 19. We know these two parameters, and we know that from Erlang B chart we can calculate the third parameter, which is the total traffic intensity A. So let us move on to the Erlang B chart. So it is here. We are focusing on the number of channels of 19. So this line here is actually indicating the number of channel of 18, and this line is 20. So this intermediate line is actually representing number of channels of 19. So we are interested in the point where the probability of blocking is 0.02. So we look at the intersection of these two, this 19 channel line and probability of blocking of 0.02, which is this point, which is shown here. So from this point we can calculate the traffic intensity. We can simply draw a perpendicular onto the horizontal axis, this bottom axis here. So it's somewhat like this. So this point will give you the traffic intensity in Erlang's corresponding to given conditions. So this one, as I said, this is actually logarithmic chart. So this dotted line corresponds to 10 and the second dotted line corresponds to 20. So this one is little above 10, so we can take it as maybe 12. So from chart we see that the total traffic intensity is 12 Erlangs for this system A, and from this condition we can easily calculate number of users, because number of users is total traffic intensity divided by per unit traffic intensity, which we have already calculated as 0.1. So if we divide them, so we get a number of users of 120 for one cell of system A. But as per given condition, we know that system A has 394 cells. So if system A has 394 cells, what will be total number of users in this particular case? Because we have 120 users in one cell and we have 394 cells in total. So if we multiply both of them, we will get the total number of users, which comes out to be 47,280 for system A. So system A supports actually 47,280 users in the population of 2 million residents. Similar solution can be done for system B. If we focus on system B, in that case the probability of blocking is again same, which is 2% as given in the problem, but the number of channels is different, which is defined by C is equal to 57. So we have 57 channels in a cell, and traffic intensity is also same as the previous case, which is 0.1 Erlang. So from data we know that the grade of service is 0.02 and the number of channels are 57. So if we refer to the Erlang B chart, we can find the traffic intensity A for this particular case. So let us move on to Erlang B chart. If you see Erlang B chart here, if we focus on the channels which are indicated in the top row, you can see we have a line for 50 channels and we have a line for 60 channels. So for 57 channel, the line would be somewhere in between, so it should be somewhat around here. So if we follow the tendency here between 50 and 60, we can find the intersection with the probability of blocking of 0.02, which we are interested in this problem. So for 0.02 probability, and we try to find the intersection of this line, which is not shown, but we can estimate that line to be somewhere here. So from this point we can find the traffic intensity by drawing a perpendicular line to the bottom axis like this. So if we draw a line here, so this point indicates the traffic intensity corresponding to the given condition of 57 channel and grade of service probability of blocking of 0.02. So as this line is 10, the second dotted line corresponds to 20, third one is 30, and fourth one is 45. So our point is almost in between 40 and 50. So we can take a traffic intensity to be equal to 45. So from chart we see that the traffic intensity carried by one cell is actually 45 Erlangs. And once we know the traffic intensity, we can conveniently find the number of users corresponding to this traffic intensity by dividing it by per user traffic intensity, which is 0.1. So we get that there are total 450 users in each cell. Since the problem states that the system B is designed with 98 cells in total, so we have per cell users of 450 and there are total 98 cells. So by multiplying these two values, we can find the total users in system B, which is 44,100. In similar way, we can calculate the number of users for system C as well. You have to proceed with same steps. As we know that grade of service is 0.02 and number of channels for system C is 100. And for Erlang B chart, which is shown here, and we have this line of 100 channels here, and from this line you can easily find the traffic intensity corresponding to this condition, which is 88 Erlangs in this particular case. So if we know the traffic intensity, total traffic intensity, we can find the total number of users by dividing by dividing the total traffic intensity by per user traffic intensity, which is 88 divided by 0.1. So we get 880 users corresponding to one cell in system C, and there are 49 cells in total in system C. So the total number of user will be 880 multiplied by 49, which comes out to be 43,120. So system C supports 43,120, and therefore total users that are subscribed in all three systems would be sum of all these three numbers, which comes out to be 1,34,500 users. So far we have calculated the number of users corresponding to each system. Second thing that we want to calculate here is the market penetration for each of the company. So we know that the total number of residents is 2 million. So we can directly calculate market penetration for each of the system by simply dividing the number of subscribers by total population. So for system A, the total number of users is 47,280, and if we divide it by 2 million, we get a value of 2.36%. So system A has a market penetration of 2.36%. Similarly, system B has a market penetration of 44,100 divided by 2 million, which is around 2.205 percent. So system B has around 2.2% of market penetration. Similarly, we can find the market penetration of system C by dividing number of users of system C, which is 43,120, by the total population, which is 2 million. So we get a market penetration of 2.156%. So in total, the all three systems, they have market penetration of 6.725 percent total market penetration if we combine all the three systems here. Okay, let us move on to another problem related to the same case of Erlang B. The problem states that a certain city has an area of 1300 square miles. So we know the area to be covered by the cellular system, and the cellular system which is used here is 7-cell reuse pattern. Of course, we have divided the area in cells, so each cell has a radius of 4 miles, and the city is allocated with a spectrum of 40 megahertz with a full duplex channel bandwidth of 40 kilohertz, and the required grade of service is 2%. And of course, for a Erlang B system, that means we are interested in having the probability of blocking of 2%. The traffic per user is given as 0.03 Erlangs. There are number of parts in this problem, so let us focus on each part one by one. We start with part A. The part A states that what are the number of cells that need to be used in the service area, because we want to cover the total area of 1300 square miles, which is the area of the city, by cells which have a radius of 4 meters. So total coverage area is 1300 miles, cell radius is 4. So what we want to do is to convert the cell radius into the area of each cell. The area of each cell is actually area of hexagon, because we are working on hexagon geometry for cells. So hexagon area, from mathematics or simple geometry, the hexagonal area is given as 2.5981 r squared, where r is the radius of cell. So this is the formula for hexagonal area. In most of the books, this formula is written as 3 under root 3 divided by 2 r square. So you can use that 3 under root 3 by 2 relationship as well. So by using this relationship, we can calculate the area of each cell, which is 2.5981, which is this factor 2.5981 into r square, and radius is 4. So 4 squared is gives the area of 41.57 square miles. As we want to cover a total area of 13,000 square miles, so the number of cells that we need to use can be calculated simply by dividing the total area, which is 1300 square miles, by area of each cell, which is 41.57. So from this relationship we get that we need to use 31 cells in order to cover the area which is to be covered by this cellular system. Second part is related to the number of channels. So the question states that what is the number of channels per cell. We know that number of channels per cell is actually dependent on the frequency reusing scheme. First thing is to calculate how many channels are there. We can see that we have a total spectrum of 40 megahertz. This is the total spectrum, and we have to divide this spectrum into duplex channels of 60 kilohertz each. So the total number of channels is actually this 40 megahertz. 40 mega is 40 into 10 raised to power 6 divided by 60 kilohertz is this factor, which is the bandwidth of each of the duplex channels. So from this part you can see this relationship, 40 into 10 raised to power 6 divided by 60 into 10 raised to power 3. It gives the total number of channels which are available in that particular system. And since we are using a 7-cell reuse pattern, so these cells, they have to be divided among the 7 cells which we have in the system. So by having 7-cell reuse pattern, so each cell in the each cell would contain number of channels which are divided by total channels divided by 7. So by dividing this relationship, 40 megahertz divided by 60 kilohertz by 7, which is cell, we get the total number of channels per cell, which is 95 channels per cell here. Okay, let us move on to the third part. The third part states that what is the traffic intensity corresponding traffic intensity for each of the cell. For this particular case, we know from part B, we know that there are 95 channels in each cell, and we are interested in having a grade of service of 0.02 as mentioned in the problem as well, and we are using an Erlang B system. So we can calculate the total traffic intensity per cell by referring to the Erlang B chart corresponding to 95 users, so 95 cells. So let me move on to Erlang B chart. These two lines, this one is 90 and the second one is 100. So 95 would be in between 90 and 100 lines, and 0.02 blocking probability line is this horizontal line. So the intersection of these two would be somewhere here, and if we drop a perpendicular to the bottom axis, so you will see that this will be somewhere here is 10, 40, 20, 30, 40, 50, 60, 70, 80. So this is somewhere around 80. So the traffic intensity we take as 84 Erlangs per cell. Okay, the next part is what is the maximum carried traffic. What is the maximum carried traffic? Because we know that we have in total 31 cells which we have already calculated, and we know that the traffic intensity in each cell is actually 84 Erlangs per cell. So the maximum carried traffic would be the product of these two, 31 multiplied by 84, which is 2604 Erlangs. Let us move on to the next part, which is what is the total number of users that can be served for 2% GOS. Number of users can be easily calculated. We already have a relationship between number of users and the traffic intensity. Simply, if we want to find total number of user, we can calculate the total traffic intensity and divide it by per user traffic intensity. For a given condition, the per user traffic intensity is given as 0.03 Erlangs. So 0.03 is per user traffic intensity, and the total traffic intensity in overall network we have calculated as 2604 Erlangs, which were calculated in part D. So if we divide 2604 by 0.03, so we get a total number of users of 86,800 in the system. Okay, next part is the number of mobiles per channel. So how many mobiles are there in a channel? So this is a very simple case, because we generally assume that how each user is having a mobile. So number of users is equal to number of mobiles. So whatever number of users we have, we can divide with total number of channels, and total number of channels were calculated here in part B. If you see, because we had this 40 megahertz bandwidth, which was divided by in 60 kilohertz duplex channel. So if we divide these two, we get total 666 channels. So we have this much of users, that means we have this much of mobiles, 86,800 mobiles, and total number of channels which are available are 666. So we can say that there are 130 mobiles per channel. Okay, this brings us to the last part. What is the theoretical maximum number of users that could be served at one time by the system? Think about what is the maximum possibility of utilization. The maximum utilization in the system will be the case when all the channels, they are carrying one user, because one channel cannot accommodate more than one users. So as if all channels in the system, they are accommodating users, so in that case we have the maximum possible numbers of users in that system. In other words, the theoretically maximum value of the number of users will be equal to the maximum number of available channels which are present in the system. So for this problem, we know that for each cell there are total 95 channels. So this C indicates the 95 channels per cell, and the number of cells in the entire region are 31. So if we multiply these two, we get the total number of channels, and in turn which represents the total number of maximum possible value of the users that can be accommodated by the system, which is 2945 users, which is represented as 3.4% of the customer base. Okay, let us now take another problem related to Erlang C system. So far we did few problems related to Erlang B, and now we are taking a case of Erlang C. That means this is a block called queued system, in which if all the channels are occupied, the new request will be put on hold. So the problem states that a hexagonal cell with 4 cell system has a radius of 1.387 kilometers. So this is the radius, and we have a 4 cell system, and for this particular system a total of 60 channels are used within entire system. So the entire system, there are only 60 channels which are allocated, and if we have to divide those channels in the frequency reuse pattern in the cluster. The load per user, or load, as I previously mentioned as well, is another term which we use for traffic intensity. So per user traffic intensity is 0.029 Erlangs, which is given with a arrival rate of lambda is equal to 1 call per hour. So we want to compute the following things for Erlang C system, which has a 5% probability of a delayed call. So there is a probability that call is delayed, and that probability is 5%. So let us start the problem. First, let me quickly summarize what is given in this problem. So the given data is, first of all, cell radius is known, which is 1.387 kilometers, and from cell radius we can easily calculate the area covered by a cell, which is by a simple relationship of 2.598 into r square. So 2.598 multiplied by 1.387 squared gives you an area of 5 square kilometer. Number of cells per cluster, because we are having a 4 cell reuse system, is 4. and total number of channels allocated for this particular system is 60. So from this we can easily calculate how many channels will be available in one cell, because one cluster is made of 4 cells, so we can calculate number of channels per cell by dividing the total number of channels by this frequency reuse factor of 4. So we get a 15 channels which are available for each of the cells. Okay, now let us move to the first part of the problem, which is how many users per square kilometer will this system support. So we want to find the number of users for this particular system. As we are working on a Erlang C system, so we have to refer to the Erlang C chart, and for Erlang C chart the probability of delay is given as 5%. So grade of service for this particular system is 5%. In other words, is 5 divided by 100, that is 0.05. The number of channels in a cell is actually 15. So from this we can refer to the Erlang C chart to find the traffic intensity. Let me go to the Erlang C chart. As we are focusing on the number of channels of 15, so we need to look for the curve. This one is the Erlang C chart, which is we need to look for the curve which is related to 15. So look at the top index, top row, which is this one is 10, this line is representing 15, and this one is 20. So this one is actually focusing on 15 channels, so we have to focus on this line, and we are interested in having 5% probability of blocking, which is 5% probability of delay, which is 0.05, which is shown here. So the point of interest what we need in this problem is the intersection of this 0.05 line and this 15 line, which is somewhat here. So from this point we can easily calculate the total traffic intensity by simply drawing a line at the bottom axis, which is actually this line is 10, so this previous line would be taken as 9. It coincides with the 9. So the traffic intensity what we find from the Erlang C chart is actually 9.0 Erlangs. As we are interested in calculating number of users, so we can calculate number of users by dividing total traffic intensity by traffic intensity per user. So total traffic intensity we have calculated from Erlang C chart, which is 9, and per user traffic intensity is already given in the problem, which is 0.029. So this approximates the number of users to be 310 users in this entire area. So this one is the number of users present in the cell, which has the area of 5 square kilometer. The question here states that how many number of users per square kilometer are supported by the system. So we are interested in calculating the number of users by unit area, users in the unit area of the system. So in order to find this number of users per square kilometers, we can simply divide the total number of users, which is 310 users in a cell, by the area of the cell, which is 5 square kilometers. So this gives us 62 users per square kilometer. So this was the first part in the problem, which gives us 62 users are supported per square kilometer in the system. Second part, it should be B, is typographical error here. So what is the probability that a delayed call will have to wait for more than 10 seconds? So we want to find the probability that a call is delayed. So we already know that the call has already been delayed, and we want to find the probability that it is delayed by more than 10 seconds. So basically we are interested in calculating that probability of delay is greater than 10 seconds given that there is already a delay. So this part, so this given condition is that there is already a delay, the call has been delayed, and we want to find that this delay is greater than 10 seconds. And if you recall the relationships that we discussed for Erlang C, we discussed that this conditional probability is given by this expression, which is e raised to power minus c minus a into t upon h. For this particular case, we know that the number of channels they are known to us. Traffic intensity we have already calculated in our previous part. T time is given as 10 seconds, we already know that. The only thing missing is h, so we have in order to do it, we have to calculate h first. H which is the mean holding time is given by this relationship, because AU is equal to lambda into h, so h will be AU divided by lambda, which is 0.029 because lambda is 1. But this 0.029 was given as per hour basis, calls per hour, you can see is per hour. So if we convert it into seconds, so we will see that this is 104.4 seconds here. So if we put these values here in the expression, e raised to power, this e raised to power minus t, e raised to r minus c minus a t by h. C number of channels is 15 in a cell, and 9 is the traffic intensity in the cell, and 10 seconds delay we are focusing on, divided by h is 104.4. so if we simplify this thing, we get a value of 0.5629, which is 56.29%. So this is the probability that a delayed call has to wait for more than 10 seconds. Let us move with the to the last part, which is what is the probability that a call will be delayed for more than 10 seconds. So we want to find the total probability that a call is delayed for more than 10 seconds. So we have already find this conditional probability that if a delay happens, so how much waiting is needed once the delay happens in the system. So we have already calculated that thing in part B, and if we multiply this conditional probability with the probability of delay, so this thing is the conditional probability. If we multiply this with the probability of delay, which is greater than 0, having delay, so we can find the total probability which corresponds to having delay more than 10 seconds. So this is simple relationships now, because we have already calculated all these parameters. This probability of having delay we have already calculated, it's not calculated, it's already given in the problem. That is, this thing is 0.05, which is 5%, and the conditional delay we have calculated as 0.5629. So if you multiply these two parameters, 0.05 multiplied by 0.5629, so it turns out to be 0.0281, or in percentage value this will be written as 2.81%. So there is 2.81% chance that a call will be delayed by more than 10 seconds. So this brings us to the end of the topic. We have in this topic we have discussed how trunking is used, trunking theory or queuing theory is used to design a system, and by trunking theory we calculate how many channels should be allocated in the system so that we achieve a specific grade of service, so that our system performs to an acceptable limit. And while doing so, we discussed a few problems, both related to Erlang B systems and Erlang C systems. We'll be finishing this topic here. Inshallah, we'll start a new topic in our next class. Thank you all.